Okay, so I've started. Bless you. All right. So I've started to talk about, or let's start coding this up, I mean. I created a quick little template inside the class code. And let's go ahead and look at what our binary tree.hpp might look like. So let me go ahead and get our ifdefs done. And while I'm doing that, what do we need to define, or what classes do we need to create for this? What's that? A node. So let's go and create that class. I'm just going to call it the binary search tree node, because I don't want to type all that out. Ooh, I need to open that back up. Perfect. Public and then private. And I do that backwards. All right. So what does the binary search tree node contain? How many of you all are logged in?
I don't think there's putty on this computer.
Yeah, I was trying to like hook up directly to the internet and it wasn't working, so I just like was sad.
Oh.
It just like didn't even show it was there. So then I tried to hook up directly from the one to the monitor and it didn't work either.
Technical difficulties. Oh good, we have salt. So first off, we need to decide what the node should represent. What should the node represent?
A small binary tree.
A small binary tree. How many elements?
One.
1. So it should be a 1. So it's going to be a binary tree of 1. What does it need to contain?
2 pointers.
2 pointers. That's these 2 guys and
Data.
the data. So we want, that's what we want our binary BST node to be. That's what we're looking for. Okay. Who's got this? All right, to help you out, type in int. All right, here we go. And that'll be the value, so whatever you want to call it. Okay. So that is this. Perfect. But now we need these 2 things. All right, someone help him out. Oop, oh, someone's got this. Yeah. Perfect. There we go. So it's got the value, you have a left, and you have a right. We have a slight disagreement on naming conventions. So I'm going to pick the one I prefer. That's fine.
Sorry.
That's what happens when 2 programmers code at the same time. You're never going to get people to agree. It's not going to happen.
The way you name things is wrong.
It's wrong. And the people have lost their jobs over naming things. Yes. Oh,
As long
yeah.
as
That
you
would
agree
not
with it.
surprise me honestly.
Well, sometimes it's really bad. Like I had one guy, you know how we do like for int I equals blah blah blah. He decided to use superheroes, so it would be for Superman equals whatever, and the next one would be like Iron Man or something. It would go down, and we're like, dude, you're a race of Superman. Like, what is going on? Yeah.
What does that
Now I
mean?
understand if you run out of letters, but if not, then use the letters.
Right. Right. All right, let me go ahead and create all of our getters and setters. Oh wait, we're doing snake case. Hallelujah. All right, get left, get right. And what was it? Oh, we need to set it too. We probably should have a set right, and then we gotta do the getter for int get val and void set val. All right, and then we need a constructor, don't we? All right, wow, that's a lot of coding, but that's how C++ likes to do it. As well as every other object-oriented language out there. All right. Oops. That didn't work out as planned. Let's try that again. There we go. Oh, that didn't work out either. That's cute. All right. Okay, so let's do the easy ones. And val equals val. Return val. OOP. Was it m right equals node, m left equals node, return m left, return m right, and then up here we need to val, we'll call it -1, left equals right, which is null, and then down here we'll call set, what was it? Val? Was that what it's called? Set val, good. Passing in val. Set left, passing in left. And right, passing in right. Okay, whew.
You missed the semicolon in the constructor after the null.
Oh, go ahead. Excellent. Haha. Let's see if that compiles. Nope. Was not declared. Hey, we forgot to include binary search tree.hpp. Wow. Almost there. Val was not declared in the scope. See how painful OOP is sometimes? Really is.
Then why do we do it?
No. You don't want to-
Because too many people agreed that that was a good way to go about it.
So they're dumb. Is what
They
you're
are absolutely stupid. Oh, they are. And now we gotta do this. We're getting there. Oh yeah, that's because the star is not supposed to be on that side. Did I miss something? Oh, I see what happened. Almost there. We're almost there. All right. You almost had me on the OOP tangent. That was pretty good. Null was not declared in the scope. So then we'll go ahead and include stdlib.h. That's a library of stds. All right. Perfect. It compiles. All right. That was.
Add in STDs first.
They make it all better, apparently.
Apparently, they just solve all our problems. All right.
STDs fix everything.
Yeah.
This is what we're going to talk about at lunch and just see how many weird looks we have.
I didn't call them that, all right? It was not me.
What does it actually stand for?
Standard.
Just standard?
Yes, that's literally what it stands for. Standard.
They could add like an
Look.
A. Or an N or something.
Or just use something else, you know.
Yeah. of all the letters they could have possibly chosen, they chose that combination of letters.
It could have been worse. I'm not sure how.
One, it's gonna be another.
What if they purposely change it to HIV?
That'd be so funny.
But it's got to stand for actually something computer, like human input validator. There we go.
There it is.
Human input validator.
First
You
job
need
you
to
go to,
petition
you need to
for
make an
HIVs.
HIV thing.
No, you call it the no. What you do is the class is called human input validator, and like, oh, okay, cool. And then
Is
your
it
first,
HIV?
and then your first instance of that class is HIV, because you got to make sure you can commit the code called the human input validator. So later, when you shorten it, no one can fault you for it. You just got to be a little tricky. Got to be just a little tricky, and then it works out.
And then every time you like talk about your code,
You're talking
at
about the
meetings,
HIVs.
It's just like, oh, so my HIV does this.
You're super,
I've been having problems with HIV lately.
you're super straight-faced about it.
Yes.
Like, you don't even notice.
Right. Oh yeah.
What if all of your code is like that?
Oh yeah.
It just, like, it's all sexual diseases, but
Oh
It
no,
doesn't
mine
even have
was
to be that. It could be any disease.
Oh, it can be anything because in my dissertation I had to talk about the performance monitoring system.
It took me a long time. It's okay.
Every
though.
female looked at me funny on that one. I don't know why.
In the project we did over the summer, we almost called it cancer. 3 of the 6 of us wanted to call it that.
Cancer?
I was just like,
Well, it's especially good if you can do it, but change the C to a K, or like change, or like make it the was it UK spelling? So like flip the R and the E somehow.
like with theater and stuff.
Yeah, or the C and the whatever. Yeah, exactly. Do that, then that just because then you're like because the first time you look at the word you're like, oh, okay, that's a normal word, and then until someone pronounces it, and then you snicker.
plausible deniability.
Exactly. That's how this works. All right, binary search tree node. Let's call it root, just for the fun of it. What value do you want to give this thing? Hey, let's give it the values up there. 5, null, and null. Okay, so we need to do ts assert root.get val is equal to 5, right?
Yes.
It's always a good idea to at least get some simple test cases going. Oh, lowercase then. Call it the BST test. Perfect. Let's see. BST was not declared in this scope. Well, let's go ahead and include it. Binary search tree.hbp. Hooray, it worked. All right, let's do a slightly more complicated test. Let's left. What do you want the left to be? Oh, we already have this 2. And what do you want the right to be?
14.
14. And then root.set left should be left. Root.set right should be right, except we want to have the address of that because we're doing all these on the stack just to be that way. So then left should be the address of left and the right should be the address of right. And let's see what happens. Hey, I like that. All right, let's
so
take
when
this.
will you set down get val?
Oh, we haven't yet. I just put those in there because of OP. It's really, well, we use set get val, but we haven't done set. All right, here we go. Let's take this one step further. Get left dot get val. Oh, it's a pointer, so we're gonna have to do that. There we go. What should that be equal to?
Left
2.
to get val.
Right, which is,
2.
how about the right one?
14.
Okay. Okay, so we have some confidence that our node is working properly. We didn't test set and get val, but we tested get val, but I don't think we're ever going to call set val, so we're good. All right, great. So let's hop back. So now that we have the node, I'm going to call it the binary search tree. All right. What should the binary search tree contain?
Nodes.
How many nodes?
As many as we
Any
pull.
want.
How many nodes should the class have?
One.
One. All right, do it. Okay, good. Someone's typing.
You're welcome.
All right, so binary search node. Let's go to the picture. We want this. What is this thing? It is a, which is a,
Move pointer.
it's that thing.
Oh, where are we putting it?
A pointer.
Yeah, it's a pointer. It's all it is a pointer. Yes, my pointers have become arrows. I don't think drawing out the numbers for the memory address, that would take way too much time. Beautiful, all right. So again, we're having a disagreement on naming conventions, but that's perfectly fine. So we're gonna have our constructor, perfect. And what else should we have? What do we want to do with this binary search tree? What do we possibly want to do on this binary search tree?
Add searching.
Remove.
You got this, go. Oh, we're not adding a node. Good start. What are we adding? It's a binary search tree of
Nodes.
no. Nodes are how, the binary search tree node is how we're holding the data. What data are we holding?
So the whole tree is a node.
No, the tree is
No.
multiple nodes. But
Point
what
to-
is the tree holding? What data is it actually holding?
Inbound.
Integers.
Yeah.
Yes, we're adding integers is what I'm trying to get at.
Oh,
So we're only adding integers, because if we were to do this with a linked list, you're adding integers. If we were to do this with an array, we're just adding integers. The node is just a way to wrap around it so that we can easily create a binary search tree. Right. So with search, let's change that to contains, because that's going to make more sense for what we're doing today. All right. Now, with remove, it's a good idea to have it be bool so we know whether the remove happened or not. That's all. All right. Well, so let me think here for a moment. Because I don't want to do your lab for you. No, I told you I don't want to. So,
It's not that he can't. Said he won't.
all right, you want me to just leave for a couple hours and come back and see what happens?
Yeah.
Well, you said the lab is getting the length. So doing these three functions is not getting like how tall
Yes, but
it
it'll
is.
get you to there so you can figure it out. It's also traversal, which is actually, we are going to do traversal. Traversal is fun. Let's see. Oh, actually, that's what we want. It's always a good idea to print something. So let's do print as
See,
well.
how exactly are you going to print it though?
Oh,
Yeah.
you have to traverse it.
yeah, we have to traverse it. All right, let's get to print in a moment. I think I jumped the proverbial gun a little on that one. That's not where I meant to be. Let's go down here. Paste that. Gotta figure out how to make that easier. All right, so on the constructor, what do we need to do?
Create a node.
Well, if a binary tree is empty, what's the root node pointing to?
No.
No. So on the constructor, we have created an empty binary search tree. So we need to set mroot to, you got this. Someone was doing it right, the other person was not. All right. Semicolon. All right, good. Okay, so of these, by the way, we are not doing remove today. This is actually a kind of a complicated one. We're also not going, it's not going to be for your lab. So I'm leaving it here for now. We're not going to touch remove at this point.
It doesn't seem that difficult though. So is it like one of those that you thought was difficult? But
What do you
it's
do
not?
to remove the 14?
You find it and then you go there
There
and
is the 7 and the 19.
How do you know it's a 7? What if there's a ton of nodes underneath the 7, but you need to maintain your binary search tree structure?
you don't care about that. You just go with it.
Would you compare,
Oh, yeah, that's why we're not doing remove today. But yeah, what were you going to say?
Would you like compare the left and right to the thing that it's pointing to?
Mm-hmm.
Okay.
Well, what's going to go in the position of the 14? In this case, you could just move either the 7 or the 19, which is great. But what if these two trees have a lot of nodes in them?
You have to do
So
it all
you're gonna have
over
to
again.
go down, bubble stuff up.
Right. You either choose the greatest of the left or the lowest of the right, and then you got to shift that back up there. But you got to take all your cases into account, because what if the left is null but the right has something? Then you have to go down the right. But what if the right is null and the left has something? Then you got to go down the left.
What if they're both null?
Then you just remove the node and everyone's happy.
That's the best case.
Right. See,
case
but
is
but
better than
but
that.
you see how Amber is an optimist? See, that's a good thing. It's a good sign. It's a good sign.
But there's no data you can't mess up.
Exactly. There's nothing there.
True.
You
Yeah,
can
'cause you can
always
break
mess
this.
things up.
You can't always mess things up. But right now we're concerned about adding. So how do we add something? What's the first thing we need to do? So we're inside the binary search tree, not the binary search tree node. Oh, but you're on the right track.
Nice try.
What's the first thing we need to do? Let's go up to the picture. Let's give me a number that makes some sense. Oh, you're not going to? Good. I'll make it a 10. We want to add a 10. What's the first thing we need to do?
Compare it to the first thing.
I'm going to make this a little easier. What was the first thing we did in the linked list?
Don't you point?
We make the node.
We make the node. Do that first. Just make the node. I'll get you started. Dynamic data structure, so it's going to have to be a node. I'm going to call it toAdd because I'm so original. All right, let's go up and see what the constructor is.
Originality shocks.
I'll copy and paste this right down here. Comment that out. All right, someone fill that in. Okay, perfect. Oops. Do we know that's going to be the values of the node to add?
It is at the beginning.
Well, just to finish this add function, are we going to have to manipulate that anymore?
Possibly.
No,
No.
because it's going to be a leaf. Because if,
It's gonna be a
remember
leaf.
in our current implementation, we just go and find the spot it needs to go and then shove it there. So right now we have a node 10 like that, right? We created that binary search tree node. What you're thinking of is something different, which we'll get to, and is actually project 3, but we won't do that today.
Yay.
No, we have to finish project 2 first.
So it's
I'm not going to give you 2, well, hold on.
Don't give him ideas.
I'll give you 2 projects only when the first project is due that day. Okay, so there's the binary search tree node that we're going to add. It's 10 with some null pointers. Let me go ahead and draw those null pointers for you. Perfect. Yeah. Now what do we do?
Now we find where it goes.
All right, how do we do that?
You have to compare each time.
All right, remember this is similar to a linked list. So let me get you started. All right, so we got a rover. Good start, yeah. If. So rover is null, that means the root is null. So what do?
We make it the root.
We make it the root. And we want to exit this function if that's the case, so
And then return.
yeah, return.
You do return.
Whoever was doing it. Great. Okay. Don't forget your semicolon. And there is an end. Okay, great. I'm trying to do work for you. I should.
Right at the end, it works perfectly.
All right. So if there's one node to add, everyone's happy.
If there's no nodes to add, am I even happier?
Actually, if there's no node, wait, hold on. If there's only one node and it's empty tree, we're happy. Great. Now you know that rover is not null. What do we do? Okay.
You compare the root.
Well, we're at rover, right? Sure, let's compare rover. And rover is a pointer, so you need the arrow. And due to silly OOP standards, you can't just go to its private data, so you have to call the function. You got the arrow right. Get val, get underscore val. Yeah. All right, one moment. Before we continue, I want to point out something. This is more of a programming technique. This is a guard. I don't know how to spell guard. There we go. What that means is this is just a guard to make sure that rover is okay. And it's really just the base case. So you don't need to think of else after this because it's returning inside the function, inside the loop. So it's clearer, in my opinion, to just after this to just continue as if everything's happy. All right. So if rover-get-val is less than 2 add-get-val, then
So if it's equal to, what side would you put it on?
what would we do? Well, is our binary search tree a set or a collection? Oh, we never decided that. Which one do you want? Do you want to allow duplicates? No? No duplicates allowed. All right. Well, let's just then, you have a point there, so let me speed this along just a little. All right, how's that?
Are we gonna need to allow duplicates later?
Maybe. Maybe not. If there's a duplicate, what do? You just choose one side or the other. But let's not allow duplicates for now.
Is there any right answer, or is it your preference?
Well, it depends on what you're holding. If you're a set, then there are no duplicates. But if you're holding a bunch of people by their name, obviously you're going to have duplicates since people can have the same name.
So it wouldn't matter if you chose left or right?
No,
Okay.
no. All right, who did that?
Me, it's bothering.
You and your exploding of never mind. Making code really long.
Space.
Well, the problem with this is I no longer see the else connected to the if above, but I think that's a coding preference. But anyways, it works. Because if you're doing that, then why is this here? Why don't we go all out?
I don't like that.
Yeah, I don't like it either.
Why'd you do that?
Why would you ever do that?
It's bad.
Why would you do that?
Because it makes it pretty.
No, it doesn't. Because really, if you're going to stick with that, you should be doing this.
No.
No? Good. All right, well, now that I'm done with my tirade. What happens in here? If it's less than, what do we need to do?
It's going to go to the right.
Let's see, if get val is less than, oh yeah, so the two adds on the right, then it needs to go to the right. But, yes,
Yes.
yes.
Now I get it.
Wait, do you have only, you have one, okay.
Oh, I thought you were talking to me. I was like, oh my
No,
God.
one braid.
Oh.
Sorry.
What is happening?
I'm just confused.
But that would overwrite the current node's value.
Is there a set right?
Yeah, there's a set right. Oh, that's what you're doing? Yes, do
Yeah.
that. Sorry.
I was like, I'm wrong. Is it just right?
Yes.
Okay.
You need to pass it what you're setting it. Okay. Now, does that make sense in our current situation?
Not exactly.
I mean, because if you're at 5, Rover's pointing to 5. It needs to go greater than, so it's going to overwrite, instead of this pointer going to 14, it's going to point to this guy over here. Is that good? No.
So we have to check the right is null.
Yes. All right, so if you set the right, then you found it, you also should return from the function. All right, but on the other hand, since you return from the function and it's not there, what do we need to do?
Else.
Let's not do an else.
You can almost hear the internal screaming.
The internal screaming of
You can
what?
almost hear the internal screaming.
Oh, who's screaming? You screaming?
You.
Oh, me?
These
Why?
Statements.
My spacing over here.
Oh, the spacing? Yeah, well, there's...
Coder preference, right?
Oh my goodness. The worst one is tabs versus spaces. Oh my goodness, these people will not stop about it. Oh my.
Are you on?
I'm spaces.
Wait, why? I feel like that's harder.
Yeah, because if you
Is
already
it-
know
is it-
tab is 4 spaces, then why hit more buttons when one button does trick?
How do you know tab? The reason for it is because tabs are not always the same.
Yeah,
It may be on 4 on yours, it could be 2 on someone, it could be 8 on another.
What?
Yeah.
So then
Mhm.
what's like the amount of spaces?
Oh,
I
yeah.
noticed it and it's really annoying.
It is really annoying. But I've configured, watch this. I configured VI. Hold on, let me roll real quick. I'm going to hit tab. It went over 4 spaces. Tab under my VI is what it does is when you hit tab, it automatically puts 4 spaces in there instead. So I've solved this problem. You can have your cake and eat it by just hitting tab. But this silliness, oh. It's okay, Amber. It's fine. We're sticking with it.
No, what bothers me the most is not having a space after if. That's what I was trying to fix.
Oh,
good with that.
I'm good either way.
Of that part.
I get that.
I get all the spaces and all the enters.
You know, I like them together.
See, I like having all the different, like, it's
So
not squished.
she likes things to come together. You like to divide them out. Okay. I think that's called the lumper versus the divider.
I think you're able to read it easier when things are a little separated.
Hmm.
It's like paragraphs. You don't just have one long essay. You have to divide it up a little bit.
Really, you're bringing English into this?
That's the quickest thing I thought of.
You really want to do that.
What is it?
Well, I mean, we
Because
do have an ethics paper due next week.
And so how does poetry abide by these
we all
rules?
know we went to this course
If you
to
do a
avoid
haiku,
English.
you enter after so long, and same thing with most poetry.
Haikus are definitely Japanese.
That's poetry, though.
It's
That's
Japanese poetry, not English poetry, so you don't connect the two. All right, person, thank you, whoever that was that started to just go forward
I
and
know, I was
ignore
looking
this
at just, like,
conversation.
copy and paste.
Yeah, you could. Oh, you probably wanted me to copy and paste, but I totally didn't.
Yeah, how do you do that like little trick you do where you like replace the word with
Yeah,
whatever you start
yeah.
typing?
Oh, CW?
C like,
C for change, W for word?
Okay, so you're not hitting control anything?
No.
Okay.
You have to get out of insert mode, though.
Oh,
So what do you... Tab. See? And it made 4 spaces for you. Wasn't that nice? All right. Nice. There, then you got to go left. If the left is null, great. All right. Oh, okay. What do we do now?
Now we don't allow the equals, so we would just return false.
We just return for now.
Oh.
All right. Well, the problem here, hopefully you can see, in our situation, it's like, okay, great. Now Rover is pointing to the, how do I get over there? 14. Right? So where do we need to put this thing in?
For a loop.
A loop! No.
That's what it is.
All right, let me help you out.
So, like, you could also do a do while, I guess. Or that works. That's it.
And I forgot how to do the whole like tab everything, so I'll just do this.
If it works, it works.
All right.
You for oh no, that works.
Well, that was fun. How are we going to test this thing?
You print it, but we have to figure out how to print it.
Okay, you want to print? We'll print. Let's do print. I like print. All right, so we're going to pause now and do print.